In this lesson, we're going to examine random variables. Our goals are to be able to calculate and interpret the expected value of a discrete random variable, as well as the standard deviation. And then we're going to review how we describe probability distributions, and this will be a flashback to our very first unit of the year. So let's establish what a random variable is. Well, it's a variable that assumes a value, so we're talking a number, based on the outcome of a random event. We're going to use capital letters, often capital X, to indicate that we're talking about a random variable. We'll use lower cases to indicate a specific value of that random variable. We'll have both discrete and continuous random variables. For example, a discrete random variable might be the amount won on a scratch-off lottery ticket. So maybe you can win $5 or $10. They have a few bigger winners of $200 and maybe a jackpot one of $10,000. So if those are your four values, I can put commas in between them. Whereas a continuous one, this is where the random variable could take on any value. For instance, if it's time is continuous, like it's not just 1 minute or 2 minutes, there's all the seconds in between, and even fractions of seconds in between. So our goal is to be able to compute both the expected value and the standard deviation of a discrete random variable. So when we're doing discrete random variables, these two formulas are given on your AP formula sheet. Expected value, immediately train yourself to write E of X, and it's simply equal to the mean. And how are we going to get the mean? We're going to multiply each outcome times the chance of it occurring, and we're going to add them together. So let's read this first scenario. On Valentine's Day, the Quiet Nook restaurant offers a lucky lovers special that could save couples money on their romantic dinners. When the waiter brings the check, he'll also bring the 4 aces from a deck of cards. He'll shuffle them and lay them out face down on the table. The couple will then get to turn one card over. If it's a black ace, they'll owe the full amount. But if it's the ace of hearts, the waiter will give them a $20 lucky lovers discount. If they first turn over the ace of diamonds, because at least it's red, they'll get to turn over one of the remaining cards, earning a $10 discount for finding the ace of hearts this time. So, what stands out to me is that I do have a random variable here. So I begin by writing a capital letter X, and it has to be a number. So I'm saying X is the amount of discount. I'm going to then set up my probability model, which I like to make 2 rows. My first row is each individual X, which is indicated with this lower I to indicate we've got the first outcome, the second outcome, the third, etc. So I could win $20, or I could win 10, or I could be unlucky and only get nothing. I also have to list the probability of this happening. So each probability I'm going to put beneath this. This is a probability model if, remember, it sums to 1 in this bottom row. All right, so the chance of each of these would probably be easiest by looking at the sample space. So I'm going to zoom in over here so that we can list the sample space and consider what happens. So potentially, what happens in each scenario is I am brought 4 cards, which are the diamonds, the hearts, spades, and my clubs. Each of these probabilities would be 1/4 chance. So I'm going to put my probabilities on the branches. Now, if I get the heart, okay, on my first draw, that means I get $20. So I know that one instantly. I'm going to write that into my distribution. The one that takes a little more thought is winning $10. How do I win 10? Well, that's the scenario that if I get a diamond, it's red, so I get a second draw. So when I have a second draw, there are 3 cards remaining. One of them is the heart. The other 2 would be spades and clubs. Forgive my poor artwork. So there would be a 1/3 chance, because there are 3 cards on each of them. And how do we do these probabilities? We multiply together. out on the branches. So this would be a 1/12 chance, would be my chance of winning $10. And then my remaining chance would be of winning zero, would be the complement. The easiest way to do that would just be add 1/4 and 1/12 and subtract it from 1. And that gives me a value of 2/3. So our probability model, if you would double check, the sum of this row will equal 1. Now, based on our probability model, we're being asked to find the expected discount for a couple. And what this means is, if many, many couples go and dine at this restaurant, how much really could the restaurant expect to pay out? Each individual couple is only going to get either 20, 10, or nothing off of a bill, but in the long run, what's the expected discount per couple, like on average? So the moment you see the phrase expected in a probability question, your brain needs to say, oh, they're asking me for the expected value, which is E of X. And you can go to your formula sheet and see that, oh, this is the same as the mean. And how do we get the mean? Well, our formula states that we take each individual outcome times the chance of it occurring, and we multiply it together. So I'm going to do 20 times 1/4 plus 10 times 1/12 plus 0 times 2/3. You want to always show that work, and then you do your math. And I get a value of $5.83. We're going to now interpret this. Now we're going to find the standard deviation of the discounts. So again, the standard deviation formula is given on the AP exam formula sheet. So when you're doing this, you want to show your work. So sigma of your random variable is equal to, you're going to subtract each X value minus the mean, square it, and then multiply it by the probability of it occurring. You'll sum all those and end up taking the square root. So here's our model from the previous screen to help us do this. So I'm going to take each X value minus the mean, which we got was 583. We're going to square it, times the chance of it occurring is 1/4. We need to sum this, so we're doing 10 minus the mean, square it, times the chance of it occurring is 1/12, plus 0 minus 5.83, square it, times the chance of it occurring. So I'm going to toss that in my calculator and get that value. And before I take the square root, I'll just put a squared on this. So a reminder, this is known as your variance, the square of the standard deviation. So I encourage you to pause your video and actually toss this in the calculator and make sure you get the same value. I get 74.306. So what am I going to do? I'm going to actually find the standard deviation now by taking the square root of that previous answer, and I won't actually round it on my calculator. I get, for my final answer, approximately $8.62. So let's talk for a second about how we need to interpret that. So not really anything new to learn if you understand standard deviation from before. It's how much the value will typically, or each value will typically vary from the mean. But again, this is probability now, so this is in the long run if many, many couples are dining. So if many, many couples dine at the Quiet Nook, their discount will typically vary by about $8.62 from the mean of $5.83. This next example is about APGAR scores, which are used to evaluate the health of newborns. So please pause the video and read the scenario you see on the screen. So the first thing we're supposed to do is find the probability that a baby has an APGAR score of 0. So when I read this, I want to make sure they've defined what the random variable is. And they have. They're saying capital X is the APGAR score, and they've set up a probability distribution for me where 10 is the healthiest a baby is, and 0 probably means that unfortunately it's a stillborn baby having a value of 0. So the probability that a baby has an APGAR score of 0 would be capital X is equal to 0. Now, how am I going to do that? Well, I know that it's probably easier in this scenario to find the complement, so I'm going to do 1 minus whatever the sum of all these values are. Now, kind of a shortcut here, rather than writing them all out, kind of a cheating way, is maybe put the first 2 or 3 up to the last value, probability of 10, would let somebody know that you're summing all of the values from 1 through 10. And you're going to subtract that from 1, which I get 1 minus 0.999 or 0.001. Next, we're asked to make a histogram of the probability distribution. Okay, so on the x-axis, this is where I'm going to put my random variable, which are APGAR scores. And on the y-axis, this is going to be my probability. And as I scan my values, I see that my highest value is 0.437. So I definitely could count probably by tenths here. And as you make your histogram, I'm almost making my little bars too high here because they're hardly even. 0.008 is so small. 0.02, 0.038. Now we're at least getting a little bit bigger, 0.09. It's finally getting close to a tenth. APGAR score of 8 is up here a little higher than 0.3, or 31%, I could say. APGAR score of 9 is like 43%. And 10 is down here at like 0.5%. Okay, so you're supposed to describe what you see. And when you describe what you see, you really should be remembering back from Unit 1 that you need to talk about shape, center of variability, and outliers. So one of the things you would probably notice right away is that this is left skewed. So I begin by getting my context in immediately. I say the distribution of APGAR scores for 2 million newborn babies is left skewed and unimodal with a single peak at 9. And before I talk about the center, because I know the median is best to use, I'm going to take a sidebar and remind you of what a cumulative probability table is. So if you're asked to make a cumulative probability distribution, all you're doing is, in a sense, adding another row to your table. For the first value, probability of getting a kid with a APGAR score of 0, the cumulative is 0.001. You're just adding your previous frequencies together. Now, cumulative right here would be add the 0.006 plus the 0.001, so it would be 0.007. And then I'm adding on the next one, so it would be 0.014 because I'm adding this, this, and this together right here. Or it might be easiest just to think for this next one, add 0.008 on to 0.014, which is 0.022. I just realized I have an extra 0 in there. Right, so I'm just going to fill in, quickly do some addition. Why don't you pause and make sure that you get the same values as me. Hit play when you're ready to check. Okay, if you've done your addition right, you will always, for cumulative probability, have a 1 right here when you get to your final outcome that the random variable could take on. So the median, remember, splits your value, your data is in half, 50% to the left, 50% to the right. So the median's occurring right here where it hits that 0.51 at the end. So it's occurring here in 8. Okay, so this is back in Unit 1, we looked at cumulative probability distributions. So again, like when you get to 10, it reaches up here at 1. So where did it reach 50%? So I go over, and that happened here down in the 8 outcome, APGAR score. It's kind of reminding you another way of viewing this would be as a function. Okay, so in my description, back to this, I'm going to say the median APGAR score occurs at 8, and I need to talk variability and the scores. The easy thing to do is just tell me how they vary. They vary, and the scores vary from 0 to 10, right? It might be when we talk unusual features, you kind of see like this right here is really where the majority of babies fall. And it would be true to say the majority because 50% we know now are above 8. The majority, most babies fall in the 7 to 10 range. And maybe rather than saying range, I'm going to say intervals, because range I know specifically means the biggest minus the smallest. Okay, so I've talked shape, center, and variability, and I've really had this unusual features in my description. Okay, so doctors decided that APGAR scores of 7 or higher indicate a healthy newborn baby. So that's good. We just saw that the majority are between 7 to 10. What's the probability that a randomly selected newborn baby is healthy? So proper notation would be capital P. The probability of X is greater than or equal to 7. So that means we are just summing these values that I highlighted, and on the exam, I would, of course, always show my work. I know it's easy just to jump to the calculator, but, if you do something silly like you hit a wrong number on the calculator, you're going to get your credit for showing your work, and they're going to recognize that you just have a simple error. So that sums to, I get 0.908. So there's about a 91% chance of that occurring. Then we're told to find and interpret the expected value. So expected value, my brain goes, ooh, that's E of X. It's equal to the mean. How do I do that? I take each outcome times the chance of it occurring, and I sum them. So here's kind of another cheat. Rather than writing them all out, I do the first several, then I put plus, I put an ellipsis up to the last one, and it saves me a little bit of time, and I would get credit for accurately showing. Somebody could figure out what I meant by that, and I get 8.128. So again, this is the idea that I'm taking many babies. So if many babies are, I should probably say randomly selected, squeeze that word in there, their average APGAR score is 8.128. So no baby gets that score. They're whole numbers that are given out, but this is the average, so make sure you report it as a decimal. So when we go to calculate and interpret our standard deviation, I'm using sigma, and what do? I take each value, I subtract the mean, I square it times the chance of it occurring, plus the next value, 1, subtract the mean, square it, times the chance of it occurring. Again, I'm going to, kind of cheat here with my notation, or be smart about it would probably be a better thing to say, rather than writing it all out. Go up to 10 times the chance of it occurring. See, I'm kind of out of space here. And I'm going to, again, maybe alter my notation and say that this is the variance, right? And type that all in the calculator, and when I do, I get my variance is 2.066. So when I take the square root of the variance to get the standard deviation, I get that it is approximately 1.437. I will show a quick second video of how you can do this on your calculator. Here it is briefly. If you are really good with the calculator, all you do is you put the value into L1, this list into L2. Let me zoom out. L1 versus L2. Run your one variable statistics. Okay, but when you do, you're running it for L1, and in the frequency, you're going to put L2. And then you calculate, and it gives you both your mean and the standard deviation we see on the screen. So if I don't get around to the second video, there it is, and briefly. The interpretation. So if many newborns are randomly selected, the APGAR score will typically vary by 1.437 from the mean of 8.128.